Okay, so good evening, everybody. Welcome to our monthly program. Thank you so much for coming out tonight. I'm really excited to kick off this season with a favorite topic of mine, geology, with Dorothy Vesper, our guest speaker. But before that, I want to share just a few updates from PBAS. So first of all, thank you to everybody that came out today. I know we have at least some in the audience that came out to our day of caring today at Yankauer Nature Preserve. So this is a big volunteer day and people took, yeah. I wasn't there, but I heard that all kinds of good things happened, removing invasives, weeding the garden, getting some really great progress on redoing the floor in our storage shed in the area that we use for like summer camps and our other programs that are happening there, new bird feeder holder, all kinds of cool things. So thank you all for your support, those that came out and those that came out here today, showing support in a different way. We're also excited to welcome back a few members of our AmeriCorps team. So those of you who have been following us over the past few months know that we've had some challenges with the AmeriCorps program. It was suddenly canceled and stopped at the end of April. It was reinstated, but kind of with some complications. But we do have AmeriCorps now. We do have a reduced amount of AmeriCorps now. So there's certainly some challenges for us up ahead, nothing that we can't meet. But we're very excited to welcome back a few members of our crew. So Holly French, who began with us in March 2024. So she's been with us now over a year and a half. And Jude Stradley, who began with us this summer in May of 2025. So this great team is going to be working very closely with Laurel, of course, who's our watershed coordinator for our fourth grade watershed program, which you don't know is a really special program that we do. We serve all of the fourth graders in the Tri-County area with a program that teaches them about water issues, water quality, the things that can help or harm water quality and environment, and things that they can do as individuals, as well as things that maybe we hope our society will do as well. So very glad to have them on our team. Upcoming in less than a month, but just around the corner, is our fall fundraiser. So fall foliage fiddles and fair. So that's going to be at Sundog's Bed and Breakfast. Very grateful, of course, to the volunteers who are organizing it, and Peggy and Sundog's Bed for our host. So highly encourage you to sign up to RSVP and join us for that fun event. That'll be lovely as always, and of course, supporting the work that we do. Another way, of course, to support the work that's coming up is the best place to get your reused, wonderful, lovely Christmas gifts, maybe, or other holiday gifts for people in your life. So right now we are taking donations for our auction. So if you have any nice quality items, we would love to add that to the collection for our online auction. So we're taking those donations until October 20th, and you can drop them off at Cool Spring or a location here in Shepherdstown. There's information and heads up our newsletter about that, but auction@potomacaudubon.org is where to email if you have any questions or just want to say, hey, I'm going to give you this thing, just so you know. Finally, I'm going to go ahead and announce our next monthly program, which is going to be Laurel speaking. So Laurel had the opportunity to go to Hog Island this summer. That's an Audubon site in Maine, and they do incredible work for environmental education, as well as just being in a magical place with a very interesting history. So Laurel is going to share with us about that place, what she learned, as well as takeaways that will enhance youth education here at our organization. So a reminder that this is Tuesday night, but moving forward, monthly programs are going to be Wednesday nights this year. So second Wednesday, so in October, that means October 8th. And now I am pleased to introduce our speaker. So Dorothy Vesper. Dorothy Vesper is a professor of geology at West Virginia University. She has a Bachelor's of Science degree in geology from Juniata College and both a master's and a Ph.D. in geosciences from Penn State. Her research is focused on water quality associated with caves, springs, and abandoned coal mines. She arrived at WVU in 2002 and has been working on springs and water-related issues in the Eastern Panhandle periodically ever since then. She originally hails from the Valley and Ridge province of Pennsylvania, where she discovered her love of springs. Welcome, Dorothy.
Thank you for that introduction. Thank you. It's a great turnout of folks. It's really fun to do these kind of things for community groups as opposed to undergraduates. They're fun, but in a different kind of way, I would say. So some of this has already been covered, sort of what my background is. And yeah, I'm a caver. I'm not a serious, okay, I'm a total pansy ass caver. But I'm really interested in caves from the standpoint of what they tell us about the geologic history, the hydrologic history, and the environment. More that than the exploration part of caving. So today I want to talk about sort of how all this fits together, geology and water and springs here in the Eastern Panhandle. We'll start with some of the geology. I like to think of us living in the crumple zone here in this part of the world, which is really what the Valley Ridge is kind of all about. And why we have all these karst and springs, really why karst matters. Why would you care at all about this sort of setting? So as Sonia mentioned, I grew up in the Valley Ridge region. She talked about this. I also spent about 15 years in the corporate consulting positions, living in Cambridge and Boston, Massachusetts. I've had an opportunity to work all over the US and, oh gosh, about 12 different countries during that time. And so the way I tend to approach things is a very applied viewpoint, as opposed to a really theoretical one, which maybe works against me in academics, but it's okay. So just to kind of summarize this idea of, that. Okay, I don't think I'm gonna be able to hide that. Sorry, did anybody hear music?
Yes, we did.
It wasn't just me. Okay, very good, thank you. So this is just a list of a lot of, really most of the grad students I've had, and they have gone half and half. So about half of them are karst people and half of them are mine water people. And I've got them color coded up here. And really, it turns out that caves and karst systems are really similar to mine systems, because once we open up all the space underground, the hydraulics become really similar, whether it's man-made or nature-made. And there's also a lot of overlap in the chemistry. So this is just a list of some of the funding that's funded by research over the years. So it's a wide range of sort of sources. Over in this area, USDA, Department of Agriculture, did a lot of work with the National Park Service along the C&O Canal. Okay, let's get to the crux of this. Here we are we've got West Virginia, we're over here in Shepherdstown. West Virginia is really the water tower of the East. Yeah, I think we'll have that menu. We can try. Sometimes you can just drag it off to the side or. Huh? From the try? Yeah. That's okay. I know. Oh. It'll work. We'll make it work. It's okay. So I got it. Okay. So I think of West Virginia sort of the water tower of the East, in the sense that West Virginia exports enormous amounts of water out of West Virginia. And because most of West Virginia, other than along the Ohio and some areas over here, but most of it's pretty rural and it's not highly industry. So we don't have a lot of contamination. So we have a lot of nice quality water, and some of it goes to the Ohio, off to the Mississippi, some of this comes right down to the James. And then of course we have a lot that comes to the Potomac. So we're really on a continental divide or a watershed divide for a lot of big watersheds. But I like the concept of the water tower of the east. Not the only one, but a pretty good one. Okay, fingers crossed.
Yes, click the screen.
Yeah, it's work. Okay, the afraid I was gonna bring back the menu somehow. That happens. So this is a geology map of West Virginia. If you're not used to seeing these, the different colors just shows the different rock formations. A rock formation is just a unit that's sort of continuous over an area and is sort of similar in geologic history and similar in origin. So the different rock units are there. The important thing I would point out on this is there's two different kinds of areas of West Virginia. So here we've got this sort of big broad area where we've got lots of different go back, big broad area with large areas of limited formations. It doesn't seem to be much going on. Whereas here in the eastern half, this whole eastern half, there are all these skinny little formations and they're bent and they're turned and they just look complicated. So one way to think about this, instead of trying to track all these little individual formations, is to think about this in physiographic provinces. And that is, it's an area that the landform and the rock structures and the geology are all sort of consistent. So this map on the left of the physiographic provinces, and here I have it blown up. And the main ones here, this is a lot simpler now, what we've got. This area in the Appalachian Plateau, which is the big flat rock lying area in the western part of the state. This mountain section is kind of a transition. This area here in purple is important, and that's what we're going to talk about most of tonight, which is the Valley and Ridge region, which is where we are here. The Great Valley, well, we're sort of out on the edge, but the Great Valley, I think of as part of the Valley and Ridge, is, just the bigger valley. And then we've got the Blue Ridge out on the far right. Now, these regions are very different in their origins and their age. So the Blue Ridge, this is up to 1 billion years old. This is really old rock on the Blue Ridge. The Valley and Ridge, those rocks formed about 500 million years ago, so they're much younger. And they're very faulted and folded. We're going to look at lots of pictures of that so you get a sense of why that is. That is the crumple zone, as we like to think of it. And out here in the Appalachian Plateau, these rocks are nearly horizontal, just sort of gently folded, and they're younger. So once we get out into the coal, the large formations of coal, there's also lots of thick bedded limestone out in that Appalachian Plateau area. But again, it's just sort of gently rolling. They're gently rolling. The rock units are very gently folded. The landscape of West Virginia is anything but gently rolling. Okay, so if we look back just at this Valley and Ridge region, and this is an aerial imagery that shows you enhanced elevation model. Look at that. Truly a crumple zone, yeah?
Yeah.
That Valley and Ridge, and you see this out your window when you live in areas like this, but I think to see it at this scale, because it extends a long way. It extends through most of the Appalachians. But it's impressive, and it's quite a bit different than the land to the right. When we go to the Piedmont and the boring sedimentary layers that take us down to the ocean, no flies there. Or those flat-line coal measures out to the west. And again, this is what it looks like. Not a strange or a surprise image for any of you who are from this area. Big wide valleys with ridges in between. Okay, so how did we get to this point? How is it that this region formed? First, we have to form the original rock. I'm not going to spend any time on that. Any one of these could take, well, we could spend a lot of time on any one of these. I want to talk a little bit about why the faults are there, and then why we see the landscape we do, which is primarily erosion. We are looking at an erosional landscape, not a formational landscape. So this is what happens when the two tectonic plates collide. This is a plate tectonics here, sort of a 101 that you'd see in your intro text. We have shallow or thin oceanic crust. We have thicker continental crust. And when two continents come together, crumple zone, yeah. So you can see the rocks in here are folded and faulted. Now, a lot of this is deep underground when it happens. So the rock is more ductile in nature, which is why we can get these beautiful folds. So the area thickens, we get crumbling, we get breaking. The folds of faults, I think, makes sense. A fault is when one rock unit travels over another. Like when I broke my wrist and this bone ended up here. I said it was a low angle thrust fault. The doctor kind of looked at me and was crazy. Yeah, that's what I got there. But yeah, so, and the upper rock unit can move tens of miles. in these. So certainly we see that. Okay, so modern day analog to this, when here's India, it's been traveling, and then eventually it's slammed into the Asian continent. And that happened, there's some dates on here, I can't quite see them. This is 30 million years ago here, 70 down here. Yeah, and what happened when India ran into Asia? The Himalayas formed. Yeah, so we have a crumple zone here, and they're still growing because the Indian plate is still moving to the north and the Eurasian plate is still moving to the south. So we have a very good analogy for what the Appalachians might have looked like 300, 200 million years ago. In the case of the Appalachians, it was the Allegheny orogeny that formed most of what we see in this region. An orogeny is just a fancy geology term, which means a period of mountain building. It's when the mountains were built. And in the case of the Allegheny orogeny, and it's one of 4 different mountain building areas that built the Appalachians. 2 were earlier than this, and it's sort of, we don't see them so much anymore. The other one had more of an effect in New England. So in this region, it's the Alleghenian, that's the important one. But what happened? North America, Africa, big collision. 2 continental masses came together, created elevated land masses, and here thickened the crust, and again, we get this thrust fault belt that runs along the Appalachians with all of those folds. So that's when those folds and all of that distortion of the rock units happened, roughly 250, 300 million years ago. If we look at the cross section through this part of the world, out here on the left, we've got that Appalachian Plateau, again, pretty horizontal. And there is the zone we're in now, and folded and faulted rocks. And then, of course, this is that boring Piedmont out here. We're not gonna worry about that because the Blue Ridge making that line, a very old rock that's been uplifted into that position. Okay, so how do you know this is true? How, other than just believing a geologist, which is, you know, I don't know. So you guys, again, if you live in this area, you've been noticing these things probably your whole life. What do you look at? Road cuts. So we get some of our evidence from road cuts, from outcrops. I'm really sorry I didn't get a chance to come over here last week and take some photographs in Martinsburg at the War Memorial Park, or at Antietam, where you can see that limestone units in stripes, beautiful striped units, because the rocks at this kind of an angle. And we get these lovely striped, a friend of mine calls them striped karst. But it's a very distinctive feature we see in this part of the world. We can look at airplane, satellite data, all kinds of stuff, and we put this together into a 3-dimensional understanding of what's happening. This is just an example of what you can see in a road cut. This one, I think it's in New Jersey of all places. Anticlines are upward folds, synclines are downward folds. We always tell the freshmen, you can remember anticlines because the A is kind of an upward fold. And here you've got anticline going into a syncline, into another anticline. You can see these on every conceivable scale. You can see them on little tiny scales. You can see them on very large scales. And those of you from this area have seen some of these on very large scales, I'm willing to bet. Yeah, so Cycling Hill, oh, we geologists, we thank God for the highway department. I mean, really, how nice of them. I can't even tell you the number of observations. So usually if you see a wreck in a car accident up there, it's probably one of the geologists. It's a really bad habit. Yeah, so Cycling Hill is a beautiful syncline. Couldn't be any prettier. And now I learned earlier that there's a connection with this organization in Cycling Hill and some springs. So I'm looking forward to getting out and doing some more things there. But here's an interesting thing. No, that is a downward bend in the rock, right? But yet it's a hill. So do not confuse the folds in the rock with the shape of the landscape, because they're not the same thing. So here the rocks are bent downward, but yet I have a hill. We call that inverted topography, where the shape of the rocks in the subsurface is inverse from the landscape that we look at. And that's because really what you see here is an erosional surface, not a formational surface. And that's true in the whole, well, all the Appalachians. A couple of geologic cross sections out of a publication. And the reason I wanted to show you these is here we've got nicely folded and faulted rocks in the cross section. But the geologist has also dashed in some lines here where those folds connect. That's what was once there, which is now gone. So what's happened is that land has eroded to this surface, and we infer what the previous folds looked like before the erosion. That's how we end up with something like Sidling Hill being a hill, even though it's a syncline.
Oh.
That's actually a nice example right there of that. We can have the other, so Berkeley Springs area, the ridge right above Berkeley Springs is actually part of an anticlinal structure. This is more common than syncline. So why do we end up with ridges and valleys? Clearly we see this. This is on a flight from Morgantown over to Dulles Airport. It's the only reason to fly out of Morgantown, as far as I'm concerned. It's better now. We have jets now. It's no longer a minivan with wings, which is what this was. But boy, do you get a good view. I mean, honest to God, we would not have gone to Dulles if he couldn't have followed Route 68. But the ridges and the valleys are spectacular when you get the view of them from the air, especially from the low air. And when we put all this together, we end up with something that looks like this kind of geology mash. This is called a synclinorium. This is the Nittany synclinorium. And a synclinorium is just a whole bunch of synclines put together where you see lots of scales. So if you follow individual folds, here's a little fold, but here's a big fold. So that you're having this overlaying of scales of folds in this valley ridge region. This is the Nittany syncline. It turns out there's also very, very similar right here in the Martinsburg area called the Massanutten synclinorium. And the map, it's got lots of the same features. Okay, so how do we end up with these valley and ridge structures? Well, it has to do with the resistance of the rocks. So rocks that are resistant to erosion stay and hold up the ridges. We call them the ridge formers. So sandstones tend to be resistant to both chemical and mechanical erosion. And our ridges tend to be the sandstone. Down in the valley, we have more soluble rocks. They have both chemical and physical erosion affects them. And so we end up with valleys. Now you look at the valley, you say, oh gosh, it's flat. Oh, rocks must be flat, right? No, that's what's underneath that? This. So you look out over the Nittany Valley, this is what's underneath the valley, but it looks flat like this. This is not the Nittany Valley, but it's the same sort of issue here in the Valley Ridge. We can go further down in West Virginia. This is from Monroe County, West Virginia. In the Audubon Society, it seems like everybody should have been to the Hanging Rock Raptor Territory. Has anyone been there? A couple people, yeah.
No.
It's a beautiful place, a beautiful view and a beautiful little hike up the mountain. But what I wanted to point out, so this is Peters Mountain, and it's right on the border of West Virginia and Virginia. And I've never taken this picture. I've stood there and taken the picture toward us over the rocks, but I never thought to walk out the rock and take a picture looking back. So I found this online, and I stood right there, and I didn't take the picture. A little grumpy about this. But what you see, this is sandstone. This is very resistant to erosion, which is why the ridge is there. It's also clearly at an angle, because it's part of a fold or a thrust fault. So it's not a horizontal rock. What you see there, that slope of the rock is the true slope of the rock. We call that the dip on the face of the rock. Now, if I look off to the right here, you can see there's some valleys and there's more ridges. If I go to the little building there and I turn around and I look out over the valley, this is what I see. This was looking north over Kitchen Creek Valley, where lots of ridges, and you can see ridge valley as we work our way out. Those valleys are carbonate rock. And the carbonate rock is what forms these karst units. Carbonate is pretty darn soluble, and so it's going to give us these nice units. So what do I mean by karst? And I'm giving you a very formal definition here because I think it's useful to look at. So it's a terrain. I consider that surface and subsurface, not deep subsurface. We geologists think deep oftentimes. I mean the top, maybe a couple hundred feet. At most, well, probably not 1,000 feet for karst. So I'm not talking big, deep metamorphic zones. I'm talking groundwater deep. Okay, so it's this terrain and it forms what I soluble rocks. And when the soluble rocks dissolve, they form all these neat little features like holes underground we call caves. I've got sinkholes up here. Sometimes you have sinking streams. springs coming out the side. To look like the ridge and valley, instead of this being one big hunk of limestone, it would need to be all folded and distorted. So we've got these characteristic features that form because the rock is soluble. And it also creates this very heterogeneous flow. So you imagine water flowing through the rock itself behaves one way. Water that flows through this can behave almost like a river. So depending on where I am in my system, water flow is completely different. This is where the overlap of my interest in mines and karst comes from, because we have the same situation. Okay, so what do we need to form a cave or a karst? This is a Butler Cave in Virginia. It's a beautiful cave system, well preserved by Conservancy. You need the right rock types. You need soluble rock. In this part of the world, they're limestone and dolomite. If we had salt at the rock surface or at the land surface, it'd be gone. On the other hand, go to Israel, go to Iran. There are spectacular salt caves. So if you're in an arid enough place, salt can form caves. Dolomite ice caves, also very similar. We need water. It's the Goldilocks water, just the right amount, not too much, not too little. And we need time. So the soluble rock, I'm gonna run through a couple chemical equations in a really sort of simple view. CaCO3 is limestone. It's the mineral calcite, which forms the rock limestone, and it dissolves and it releases calcium and carbonate, which are both dissolved in water. So I take a solid and I put it in water. All three of these pictures are different places in the world where karst is formed from these soluble rocks. And you can see these beautiful sort of water etchings, sculpting of the rock. You can see it up here, sort of smooth side. This is the burn in Ireland where the rocks are cracked and then you open up these joints in the rock, creating a beautiful pavement. This is a UNESCO World Heritage Site in Madagascar, which are spectacular limestone pillars. I haven't gotten to that one yet. Maybe someday. We can think of this in a slightly more complicated chemical formula where we take our mineral calcite and we let it react with carbonic acid. And carbonic acid just forms when rainwater interacts with CO2, even background CO2 levels in the atmosphere, and it rains down on the rock and leaves dissolved stuff. So you can think of rainwater and rocks, it's like a giant titration. If you remember doing a titration in an intro chemistry class somewhere along the way, where you drip acid on a solid, or you drip acid in, that's all of karst. It's a big giant titration. Rainwater, slightly acidic, dissolves rock, which is slightly basic. And we get dissolved stuff. This reaction goes both ways. So we can take it from left to right, and what happens when I take the rock and dissolve it? I can form caves, which is a nice thing to do. I can also let my stomach acid to dissolve tums, which are made of pharmaceutical grade limestone. That's real. With a little sugar and flavor. Well, okay, a lot of sugar and flavor. The reaction can also go the other direction. And it might form beautiful cave decorations. That's how that happens. It might be used by biological systems to make shells. It might form scale in your pipes, which we are less fans of. Or when you boil your tea kettle in this region and you finish and you notice all that white powder, or the ice cubes evaporate and this white powder at the bottom of the ice cube tray. Yep. That's this. Exactly what's happening. So what other features do we see in this region associated with karst? Well, one is sinkholes. This is the map of your sinkholes. So this is hot off the press. This is a grant we just finished and sent the final report 2 weeks ago. The grad student who did a lot of this work just got the okay today from her committee members to defend her thesis for her master's. She's now working for the West Virginia Geologic Survey. This was done with LiDAR data, which is a remote sensing technique. My friend who is really good with that kind of stuff wrote some machine learning code that took this and turned this into a map. And then a whole army of undergrads and graduates went in and looked at every one of these individually. Wow. And remapped them by grids twice. Wow. Wow. Yeah, we paid for a lot of undergrad beer drinking events like that. Just to make sure you're sort of where we want to be. This is Berkeley Springs, the ridge above Berkeley Springs. This is Back Creek. Beautiful syncline in Back Creek. And this is North Mountain coming through here, and then out here's the Blue Ridge. So yeah, there's no shortage of sinkholes in this region. But I'll tell you, Greenbrier is way ahead of you. So this is the density map of sinkholes statewide.
Wow.
So Greenbrier and Monroe County are definitely the winners or losers, depending on how you view this. Pendleton County, this is Germany Valley, which has got a lot of caves and a lot of really spectacular karst in Germany Valley. And, you guys are doing okay up here. I don't know if you want singles or not, but. I would say there's probably a little bit of bias in this only because, so LiDAR data lets you look through trees and vegetation and you really can see the land surface, but you can't see it through concrete and buildings. And so the fact that there's more buildup in this region probably creates a little bit of bias in the data set. But it doesn't account for all of this. Cave density. Well, I'm sorry to say you didn't get any green on the map for this one. Most of the cave density, the highest density is down in Greenbrier County. Two things. One is it's real. Greenbrier, that part of Greenbrier is in the flat line units. The limestone in the Greenbrier County can be 1,000 feet thick or thousands of feet thick. So there's lots of room to make caves. Okay. In the valley and ridge, our limestones are smaller and they're folded and you just can't extend your caves as far. So part of that is just real and dictated by the geology. The formation that forms the caves down here is basically the cousin to the formation in Kentucky where Mammoth Cave was. Very thick limestone, just the right conditions. Okay, so the other bias though in this is, where do cavers go? Where do the caving clubs have their houses where they all spend time? Where did cavers buy the land? Yeah, so there's a really high density of cavers, but you go down and you stay at West Virginia Association for Cave Studies, Caves and Karst Studies, WEVAC, has a nice field facility down there, and you see caving and student caving groups from New Jersey, from New York, from DC. They go to Greenbrier County, so there's a bias in the sampling data for sure. This data though comes to us. Marissa is the one who's about to defend this data as part of her thesis. The data comes from one of the other grad students who happens to be a non-traditional grad student who is headed to the West Virginia Speleological Survey. They are the organization that keeps all the cave maps and all the cave data for the state. And it can be a little hard to get hold of that. This is very general. We wouldn't be able to put exact points on. They would not want us to do that. But it's a nice data set. Okay, so springs. That's really what we're interested in tonight. Where do springs form? So this is my valley and ridge diagram. This comes out of a little paper a couple of us wrote, kind of a concept paper a few years ago. Up here in the ridge, we have sandstone. On the sides of my ridges, I tend to see a lot of shales and some mixed units. There's maybe a little limestone mixed in. And then down in the valley are the biggest extensive carbonates, primarily limestone, but also some dolomite. Where do we find springs? You find a few up in the sandstone, and they're a treat when you find them. I gotta say, they have beautiful quality water. They're just little sweet little things. It was one of those where I broke the thrust ball and wrist. In this zone, we have a lot of springs that are very small, very ephemeral. We had a grad student walk up and down Peters Mountain one summer, all summer long, and he counted like 300 little ephemeral springs. Yeah, and if you look at the map of Monroe County, there's a whole lot of springs in this one little area. That's because that's where Jeff walked up and down the mountain also. We were talking earlier about boulder springs, and there are these boulder fields in the mountain that also sometimes issue for springs. And boy, we don't understand them in any kind of quantitative way. They add to the storage capacity of the water on the mountain. They add to the water flow. They create springs. And we don't understand how they function really. I've talked to a lot of people that have sort of toyed around with it, but no one's really looked at it very closely. Down here in the valleys where the big springs are, and that's where most of the springs are. So in the carbonates, we see lots of springs flowing together. Here I've also added a deep thrust fault. This one will come up, and perhaps if the water flowed from very deep, I could have warm springs. We've got lots of warm springs in the Appalachians. We don't really have springs, not like Yosemite. But look at Berkeley Springs, it's about 70 degrees. You can go down to Warm Springs and Hot Springs and Warm Springs, Virginia. Go down to Monroe County, right? Practically, you can look down from that view from the Raptor Observatory and see Old Sweet Spring and Sweet Collegiate, which are a series of old warm springs. Many of these were spas pre-Civil War time. So they often have interesting architecture and interesting. So we've got all these different kinds of springs here in the bigger area. We did a bunch of work here in this valley. So this goes back to early on when I was first working at WVU. And we had a couple projects, which we got a big grant from the USDA to look at drought in the groundwater in the Martinsburg area. And the day it arrived, it started raining. It's a mistake to write a grant specific for these stream events, I've learned. So here, just to orient you a little bit, this is the Opequon Creek watershed coming up to the Potomac. Tuscarora Creek is a little creek here. It flows from up here. This is the base of North Mountain. So it flows from the base of North Mountain, it takes a right angle turn, and comes across into Martinsburg. If you've never driven Tuscarora Pike, that is a beautiful little drive. Beautiful area. We like it because it's a very nice, small confined watershed. So here's the geology map for the Tuscarora Creek area. And here to the west, that's North Mountain, which is got sandstone on top because it's a ridge. It's very steep. There's not a lot of shale there. And over here, this is the Martinsburg area, and this is on the Martinsburg Shale, which is not a carbonate. It doesn't form karst. If you look at a map of the geology of the area, you'll see this band of the Martinsburg Formation shale going right down through the Martinsburg area. And that's what the Opequon Creek sits on. Okay, so if I follow Tuscarora Creek, it flows along here, base of North Mountain, takes a right-hand turn and comes down in here into the Martinsburg area. And there's some interesting things. One is the density of springs. So here, close to the mountain, there's a lot of springs. You're looking at the circles, and there's lots of little circles along here. There's quite a few here. We call that Burkhart Corner. That was Burkhart Farm. There were like 3 different Burkhart families all in that corner. And then along here, there's springs, but there's not quite as many. This here is Kilmer Spring. That's right by War Memorial Park in Martinsburg. You know where that is. Okay, so what was interesting to us about this? One is the distribution of springs. We've got lots of small ones up here, but there's lots. Poorhouse Farm, if you've been to Poorhouse Farm, and there's a spring house right there, it's one of these right in the series. I think it's probably that one. But as we come along here, they're bigger. So Kilmer Spring, by the time we get to number 12, which is one of the water supply springs for the city of Martinsburg, that's a big spring. And even during drought, it flows. I mean, on the order of millions of gallons a day. So the question is, why was this? It has partly to do with the structure that we have some faulting through here, but also the fresh water that comes down off the mountain is chemically really aggressive. We often see this in the Valley and Ridge, where we get a lot of springs right at the base of the mountain because the water from the ridge is chemically aggressive and it's really good at dissolving the rock. So we get bigger open systems right at the base of the ridge. Looking at the cross section again, you can see here's Tuscarora Creek, what it looks like, and this is the Matanuska synclinorium. North Mountain over here. Notice these big sort of faults. These are just breaks in the rock that come up here very close to North Mountain. Probably a little bit to do with why North Mountain's there, but that's why we think we have lots of small springs. The rock is just broken up over there to a greater extent. And then the water flows across here. You drive that Tuscarora Pike, that road, I challenge you to drive that road sometimes this week and think, what does it look like underneath? Because it just looks like rolling hills as you drive along. Sort of a nice undulating surface. You wouldn't think, oh gosh, everything's all folded and distorted underneath. So just to show you what some of these springs look like. So when you go hunting for springs in this part of the world, what do you look for? Yeah, look for spring houses. And you look for old stone houses in the States. Because why? These people settled where the springs were. So the history and the development of this region, and we see the same thing in places like Missouri, which are incredibly rich in springs. People built their farms where there was water, and they saw spring water as being less flashy, more continuous. It was a good source of water, and because it's groundwater, it was safer. And we see that often. This one down here, these are all private properties owned by different landowners who graciously allowed us to come and visit their springs on a regular basis. This is one of the spring houses at Kilmer Spring. It's the most unassuming little thing. There's about 3 of these in the field together. And again, they produce millions of gallons of water a day. Doesn't matter if there's drought, doesn't change. Changes very little. Yeah, so That's what I find when I go looking for springs in this area. And they're beautiful structures all on their own, absolutely gorgeous. There are some natural springs in the area too. This is called Snodgrass Spring. Well, it's either big or Snodgrass. They're side by side, and I've never gotten a definitive answer from anyone. If you know where the Big Springs Veterinary Clinic is, on Route 9, south of Martinsburg, just south of the quarry, right behind the vet clinic. It's a beautiful spring. It used to be a water supply for Martinsburg, but then Martinsburg gets water from the quarry now. It's beautiful quality water, and the quarry's got to de-water anyway to be able to mine. What better use than to use it for public water supply? Okay, so good, we're in good time. How important is all this karst stuff? I mean, it's all very well. I like springs. It's hard not to like a spring, really, I think. But what about in the bigger picture? Well, a lot of the US has got karst. This is the US karst map put together by the Geologic Survey. Also want to point out down here, Puerto Rico has major karst belts. I do a lot of work in Puerto Rico because there's terrible contamination in the karst, that northern karst aquifer in Puerto Rico. It's on the northern belt where pharmaceutical companies went in there for a tax break. And where did pharmaceutical companies build? They need a lot of water. They build on the karst aquifer because they're prolific aquifers, and there ended up being a lot of contamination. It's the highest density of Superfund sites in the US. All in that little region. And there are certainly health issues related to that. So that's a project I work on, associated with NIH and people at University of Puerto Rico. What's it? University of Puerto Rico. As my friends there would say. So all of this, yeah, karst. Imagine you're from Florida. I mean, we have a little bit of karst here. Look at our little valley and ridge. Florida, enormous karst. These regions, that's a deeply buried karst in the Midwest and up into Wisconsin. Missouri, a lot of karst. Or this is the Edwards Aquifer, which is one of the best understood aquifers, certainly in this country, maybe in the world. It's got a lot of attention paid to it. San Antonio over here, Austin over here. And they pay a lot of attention to that aquifer. The Edwards Aquifer Authority is top notch. The estimates that are as high as 40% of the people of the world drink their water from karst. It's a lot. Yeah, so this is not just, oh, it's pretty in our valley. It matters on a world scale. Here on a world scale, okay, North America's got a fair bit of karst. Other regions, it turns out Europe has quite a bit of karst, and there's been a lot of study of that. The other is Southeast Asia. Guilin, China, in the Li River, Ha Long Bay in Vietnam. Do you see the tower karst? I'm sorry, I didn't put a picture in. If you've ever seen the movie, well, like half the James Bond movies, go there. I can do all, the King Kong movie, Kung Fu Panda. When I teach my karst class, I do a whole lecture on movies set in karst topography, and there are lots of them because it's beautiful. It really is. And in fact, it's so beautiful that there's a lot of UNESCO World Heritage Sites that are karst. In fact, UNESCO World Heritage Sites on their website, look at this. World Heritage Sites featuring caves and karst scenery. Yeah, they're spectacular here. And I showed one of this earlier. This is the Burn in Ireland. It's on the west coast, just south of Galway in County Kerry. The glaciers have stripped the soil off, and so the limestone has been exposed for a very long time. And because of that, we have all these little solution cracks in this. And an enormous number of the endangered species of Ireland live in this setting, because it's a very protected setting. This one on the right, this is Plitvice National Park in Croatia. Okay, I don't know that it's really pronounced Plitvice, but as far as I can understand, unless you were born in Croatia, you can't say it right. Everyone I met in Croatia tried to convince me of that, I'll say that. This is a spectacular place. You've been to this site?
Yeah.
Spectacular.
Yeah.
For me, it was sort of a bucket list place. My bucket list all kind of is related to karst. Fortunately, I have a husband willing to join me on these adventures, although he's a psychologist. I took 7 psychologists on a field trip to this area. And somewhere there's a good joke about a geologist and 7 psychologists go on a field trip. And I've never figured out what the joke is yet, but I know there's a good one. So But Beach, so it's a whole series of waterfalls, and you can walk this boardwalk through them. And it's degassing CO2 and precipitating tufa. So travertine is when limestone precipitates out from hot water. Tufa is when it precipitates out from cold water. And there's a lot of biological activities. There's a lot of moss and, oh, it's spectacular. It's an amazing place. So yeah, there's a lot of beautiful karst sites out there. And again, water supply. So here are 4 cities which are almost completely dependent on karst water. San Antonio, add Austin in there as well, that whole distance, San Antonio, San Marcos up to Austin, all are on the Edwards Aquifer. Vienna, Austria, their primary water source are the karst springs in the high alpine valleys of the Alps. But they are limestone karst springs is their primary source. Rome, Italy. Think about this. During the Roman aqueduct building, what were they connecting to Rome? Springs.
Right.
Yeah. So Rome has a whole long history of association of water springs. And Damascus, Syria, that's a huge spring, fledged spring. So Damascus is the oldest continuously inhabited city in the world. It's the 3rd largest spring in the world. I don't think this is coincidence. Think about this, very arid climate, arid region. Where do you settle? You settle where the water is. You have a spring that's that big. It's a good water supply. Yeah, so again, this whole history, and we can look at, well, this again would be a lecture in itself. But certainly that where people have settled, where people have felt the water was worthwhile, has been tied to springs. And I also want to mention that springs form this really special ecosystem, it turns out, because springs are a window into the groundwater. So if you look at spring water, it's different than stream water. It's more consistent thermally. You're actually getting all this input from the groundwater. So it tends to be more, they tend to be nutrient poor because groundwater is nutrient poor compared to surface water. But you get a window into the subsurface. So here, how well can you see this little guy? A little bit? Okay, good. So that little guy on the left, he's just a little critter who came out of a spring. But he doesn't live in the spring. That's a subterranean cave. That's a troglodyte. So there's a couple features here. And this is actually one of the springs on the C&O Canal. 80% of the rare, threatened, and endangered species in the state of Maryland are found in the springs and caves of the C&O Canal. Okay, granted, they've looked a lot more. But still, there's a lot there. This little guy is a rare, threatened, endangered species. And there's 2 things I want to point out that we see in subsurface species. One is he's translucent. You can see right through him. That black thing down the center, that's just yesterday's lunch. But when you live in the subsurface, you no longer need pigment. You become translucent. We see that regularly in subsurface species. The other thing is, look how long. He's long, but his appendages are long. Look, I don't know which end's the antenna and which end's the legs here. I'm no biologist. But the things sticking off both ends are kind of long. And we can look at species that maybe have both a subsurface and a surface. A species that can live in both places. And the ones that live underground are elongated, they have elongated appendages, and they lose their pigment. Sometimes when they come back to the surface, if they're bred on the surface, they can re-express it. So sometimes it has to do, the genetics get rid of the ability, and sometimes it has to do with gene expression. And we learn a lot about genetics by looking at cave species. But often we see them in the spring. The Park Service said, oh, we don't want to tell people where there's endangered species because they might go collect them. Well, I hate to say this, but a cave dweller who we found in the spring is he's on his last days anyway. This one on the right, this is a snow trillium. This is a little tiny white trillium, it's about this big. And it blooms in the snow. They're only found in a few places of the world. Where they're found, they're prolific. And they're found near springs. And there's a big set of them, a couple big sets along the Potomac. And if you catch them right, you can see thousands of them in the snow. Like you don't want to step on these poor little things. You know, they only live in a couple places in the world. The last thing I want to do is stomp on them. But they're beautiful little trilliums. So again, it's an unusual ecosystem. And let's not forget this guy. Who lives in the springs of Florida? It makes good use of that warm spring water in the winter, or the consistent chemistry and the consistent water in the springs. So springs do form these very nice ecosystems that are a little bit different than surface water, and a little bit different than caves. They're somewhere in between. So I think with that introduction to this idea of spring as ecosystems, I will say, I am actually looking for springs right now. For the next year, we got some funding to do spring ecosystem assessments, in which we'll go into a spring, we look at the water chemistry, we look at basic water quality, and we look at the ecosystem that lives in the springs. And I just learned today how much the Audubon Society here, Potomac Valley, has preserves and has springs. So I'm really super excited about that. I think you guys might all see more of me than you want. But I do also ask if you happen to have a spring on your property, or if you know ones nearby that are public ones. We're always trying to locate ones, particularly ones where people know something about them, for sure. So with that, I have a few minutes for questions, and thank you for your time and attention.
Potential water bottling facility in outside of Middle Way. And
I don't.
it's right off of Newtown Road, going into Middle Way.
Okay.
There's a proposal to generate, I guess, something like 500,000 gallons every day of water. And just the negative effects of that with the wells and.
Yeah, I don't know any of the specifics about that. I remember, I've heard of it, that this is going in.
Yeah, it's in litigation now.
Yeah, but I don't know any of the details about it. I'm sorry. As far as how they're extracting, there's certainly places where you can take lots of water out of your spring with no harm. There's places where, I mean, like Poland Springs was in litigation for many, many years in Maine for extraction of the water in that area. So I don't know any of the specifics to really comment. I'm not gonna even try.
At Canadian Valley State Park, there's a trailhead. The trailhead is behind the golf course where you would park if you're going to be golfing. It goes down toward the stop headwaters in the Blackwater River. When you get down there, there's an area that's smaller, but it reminds me of the photograph of that site in Ireland. Looks like
Oh,
gravestones.
yes.
Is it the
Yes.
same? Is it the
Same
same
type of
thing?
stone? Okay.
Yeah, and it's a very similar formation.
It is.
I don't know why there's no soil in that location, and I've never been there, but
It's
just
really
like the
cool.
past couple weeks, I've had like 3 people send me photos of it.
Oh, you gotta go see
You
it.
gotta see it.
It's really
Yeah,
cool.
yeah, very similar
It looks
to
like-
limestone pavement.
It looks almost like a graveyard.
Yeah, it's
Like
amazing.
walking
It's
on
like
all the
that.
stones.
Yeah.
Yeah, you really get a sense when you see that, those rocks have really consistent angles to them.
Yeah.
So you tend to get them either at 90 degrees or 120-60 pairing
It's real like-
of folds.
Nice.
Yeah, very consistent. And that has to do with the stress fields. And it turns out those stress fields go all the way back to that collision with Africa in some cases. So even if that area wasn't really influenced by the collision, the forces extend well beyond the crumple zone. And we've discovered this looking at the sinkholes and the elongation and the orientations of our sinkholes. We were really surprised, to be honest, and we had to drag in our structural geologist who looks at these kinds of issues like tectonic forces. And he said, yeah, the force basically extends over. So even in Canadian Valley, I wouldn't be surprised if you see similar orientations in the breaks and cracks.
Yeah.
Is what you see even here in the east.
You said something about when in Syria, that was the 3rd largest spring in the world. Where's the number 1? I'm just curious.
I don't remember. I can tell you, so the largest springs in the US may surprise you a little bit. Probably doesn't surprise you that Florida has some of the largest. So we talk about first order springs being the really big ones. Florida's got some, Missouri has got some enormous great springs. Big Spring being a popular name for springs. Right up there with Blue and Boiling. But the other place we see a lot of great big enormous springs is in the Pacific Northwest. So an area of the Columbia River basalts, where there's all these basalts, and in between the basalt layers, the rock is all fractured, and all those big waterfalls that come out of the cliffs along the Columbia River, those are springs. And they're huge springs. They're not limestone, They did not form because of soluble rock, they formed because there was a layer of basalt was created. And then there's a while before there's any more basalt. So what happens is that top of the basalt breaks up and it weathers in the air. And also because the top layer is exposed to cool air right after it's laid down, it cracks. And then we put another layer of basalt on top. So what I have, the top of it cracks. That cracked zone at the top of the basalts is really permeable. We can move a tremendous amount of water. So all of those big waterfalls that you see along the Columbia River gorge are flow coming through what's called the interlayer between the basalt. And those are some of the biggest springs in the country as well.
Does it have salty taste to it, or is it pure?
Shouldn't be salty.
You said it's between the salt, I don't know.
Between basalts.
Basalt.
The lava
Oh,
layers.
sorry.
Yeah.
I did not know.
Yeah. Sorry, the lava units. So the lava units are made of rock basalt, whereas the Brits would say basalt. Basalt. Yeah, and they don't dissolve much. So that water chemistry is very unsalty compared to here.
I don't remember, sorry, somebody else. Anyway, I don't remember what the map was for Africa and, South America, but along the Congo River, which is one of the longest rivers, they have tons of waterfalls and things along there. And then, the Amazon, is there karst there or not? Or
There's
when-
not very much karst in South America,
that
or
would
it's
be-
not been mapped. So if you look at the world map, South America is the probably karst poor region
Okay,
of the world. I suspect it has, so South America though, has got a pretty complicated tectonic history with collisions and, you know, the whole Andes Mountains and then rising up because of the collision of the Pacific plate and the South American plate. Yeah, tectonic forces. And I think it probably has more to do with elevation change and drop. So it's
Right.
not necessarily limestone.
right,
So we can get these big waterfalls and big springs even when we don't have limestone.
right. Thanks.
I had someone over here in our,
When we were in Hawaii and my son has a property there, the hot springs they have is usually it's really close to Vancouver. We live up towards Berkeley. I've heard so many reasons as to why the temperatures of their water there is so consistent. It's like the groundwater should be like 50, 55, and it really, it's always in the mid-70s. So I keep saying, well, there must be some magma or I don't think it's a chemical reaction, but it's a,
so the Hawaiian island chain, and don't mean just Hawaii, but going all the way up through the Emperor chain, which goes all the way up to the Aleutians.
Right.
Where Hawaii is now, where the active volcanoes is sort of a hot spot. And so as the plate rides over, it forms volcanoes when it's over the hot spot, and which is why we have this long chain, is that plate has moved over and moved up there. So I think it's just a high geothermal energy right in that area.
Right.
Right. And geothermal fields are not like completely consistent. So you tend to have a little more heat over here, a little more heat over here. There are plenty of places, even just here in the region, where we might have warm springs and cold springs, like here to the end of the stage, where I can have a warm spring and a cold spring side by side. So the heat does not come up in a uniform way, and the water also does not come up in a uniform way. So for water to be warmer than ambient temperature, that is the annual average temperature, which is what groundwater usually is. But if it's warmer than that, it has to have, almost always has to have flown deeply and been affected by deep temperatures in the earth. Now, in some places, we have a high geothermal gradient, meaning that the earth is just a lot warmer. But again, it's just not that consistent over short little places. So I'm happy to say there's a hot spot that's created the Hawaiian chain, but whether this town or that town has warmer water.
right, yeah, so Berkeley Springs itself, that spring there in Berkeley, it's always like 25.
Oh, here?
Right.
Morgan County. Oh, okay. Yeah, so Berkeley Springs is interesting. That's another one we've done a little bit of research on. So people say Berkeley Springs flows out of sandstone. Okay, Berkeley Springs flows out of sandstone. If you look at Berkeley Springs, there's sandstone right there. But it doesn't flow from sandstone in the big holistic picture. That water has to have flown deeply to warm up. And I think probably it's the fact that there's a high enough mountain beside it that you need that hydraulic head or that forcing, it's a pressure forcing of the high water forces the water deep enough. And the fact that there are a lot of very deep fractures in that area that allow the water to travel very deeply. Now, the fact it isn't warmer, it might be that it's not that warm at depth. It might be that it didn't go deep enough. Or it might be that it went deep, but it came up slowly enough that it cooled a little. Or mixed with cooler water. So it's, you don't always know. I do know that the water at Berkeley Springs has been underground for a fair time. The USGS has done some water sampling there where they look for tritium. So all groundwater or all water, if it has been on the Earth's surface since the early bomb testing, groundwater that has been underground from prior to that time does not have measurable tritium. So you can do sort of this before or after, and we know that water's been underground at least long enough not to have tritium in it. Well, you can look at aquifers out west where the travel time is 1,000 years, so locally for this region, that might be a long time. And it also suggests deep flow.
Yeah.
Old Sweet Springs down in Monroe County, there's no tritium in that water either.
Question about the depth of line. Are you pointing at me or?
Yeah, I'll do first. I feel bad that I keep waiting in.
The depth of limestone in our area, the Maryland Geologic Survey has a transect that runs through Hagerstown and Antietam. And they estimate that the limestone in that area is 6 miles deep. So, and that's an estimate, of course, because nobody drills
Yeah.
6 miles.
Yeah. There's a certain, what we tend to call geofantasy when we draw those diagrams. So geologists tend to be skeptical of the deeper diagrams. With that said, it's not impossible.
Right.
And also keep in mind that the rock can be at a very high angle, in which case maybe the rock thickness, that unit, when it formed, it was a thin little unit. But now I put it vertically and I drill there and it's very deep.
But the Great Valley is really the ocean bottom, but the Rake Ocean when Gondwana and Laurentia pushed
Mhm.
together. So there was a lot of piling of limestone
Yeah.
together, that could make it thick.
Very deep, yeah.
Yeah.
Yeah, absolutely. And there are certainly areas where there's very deep limestone in the Appalachians. So what it's referring to, when the two continents were sort of side by side and coming together, there was a shallow ocean between them where we accumulate a lot of sediments. And that's part of what gets squished together in that whole crumple zone. And plus, remember, Allegheny wasn't the first orogeny. It was like the third one to form the Appalachians. So we big build mountains, but we didn't have big mountains left. So what happened is they eroded down and all that sediment and those talus slopes and the alluvial material that came off all those previous mountains was also in those basins. So there was a lot of extra material there. And yeah, a lot of the limestones came from that, but a lot of the other rocks did too. Okay,
Is there a connection between aquifer and karst and springs?
yes. So an aquifer is a water supply in the groundwater. So it's a groundwater, but there's an economic connotation to an aquifer that is sufficient water can be extracted to be used for a water supply. Not necessarily public, but even just a private. So an aquifer is anytime I have groundwater of sufficient pumpable quantity. It can be karst, it can be anything. It can be sandstone, it can be shale, it can be those boreal alluvial sediments. They've got lots of aquifers down there. Springs are defined as any place groundwater intersects with the land surface. So it can be in these karst settings where a stream flows out of a cave. It can be a vernal pool where water comes up. It can be flowing in between lava layers in the Columbia River basalts. It can be, we mentioned Hawaii, we have what we call pseudokarst, where the lava tubes leave holes underneath, so springs can form in any of those. They're like, karst forms from dissolubility or soluble rocks. We might say pseudokarst if it's got these big holes underground for some other reason. So these are like, this is like You know those Venn diagrams where they overlap every possible way? So all three can be in the same, but they don't have to be? Does that answer your question? Yeah, think of a Venn diagram with 3 circles with every conceivable overlapping combination. Because the definitions are sufficiently different. Yeah, okay, this one first.
So, two things. One, with that definition of spring, if water comes up from the groundwater source, but then continues and flows downhill and becomes a stream,
Yeah.
is it still a spring? The origin spot, or is it just the headwaters of a spring?
I think of the spring as right where the water comes to the ground surface. Sometimes people refer to that stream afterwards as being the spring run,
Spring fed.
which you see, or a spring-fed creek. A spring, the water from a spring, I think of as truly groundwater, so chemically, ecosystem-wide, it doesn't have influences of things like sunlight. So once you get into a zone where sunlight and plants become more important, I think of it more as stream, but I don't think there's a fine line to it.
Right. You can't see the border, I'm sure.
Yeah, it can be hard to decide, and we're doing this with the spring ecosystem assessment. The first decision we make is what area are we doing the assessment of? And I'm like, oh, it's there, and the biologists are like, it's there. I'm like, there's plants, it's not a spring anymore, it's photosynthesis. None of that in the subsurface.
And you said you were looking for springs, are you looking for them, in any state, I mean, like, not state, like Maryland or Virginia or,
Yeah, close enough that we can send the students out easily
okay.
on a limited budget. So in a regional area, and I've sampled, we go over to Warm Springs area, down Monroe County, West Virginia. We cover most of West Virginia. I go up to central Pennsylvania and sample up there. Okay, there's another question here.
So it is an artesian well, a spring with a lot of hydraulic head or something different?
Yes, and the distinction, so an artesian well is anytime the spring water comes up with sufficient pressure that the water elevation is above ground level. So it's a hydraulic pressure control, but it needs to actually come up out of the ground, above the ground. Which of course, if you have a pond, it's gonna go every which way. If I have a well, I can tell if it's artesian flow because I put a well casing there, and if it comes up to my top of my well casing here, it's artesian. So yeah, it's a hydraulic control, but the definition of artesian flow is if the pressure head is higher than the land surface. Hard to tell in a spring if it's spreading out, but you can if you could control it, put a well casing around, you can tell. Okay.
I have a question from Zoom and a comment. Deborah says, very interesting talk, thank you. Where can we find some of these geological maps with the local rock formations? And then she also had a couple suggestions of local springs, which I'll show you afterward.
Okay, finding geology maps. I would look either at the state geological surveys or the US Geological Survey. They actually have the whole country online that you can put a little box around your area and pop up. It's an interactive map. So I would probably go to, get what it's called. If you look up USGS Geology Map Interactive, you would be able to find it.
Thank you.
Yeah. Thank you for the question.
You're looking for springs, there's at least one in the Potomac, right off our property, that's also an artesian.
In the Potomac?
Yeah.
Oh.
Bubbles up from the stream beds in the Ford.
Interesting.
So you can walk around the Potomac, is about that water temperature most of the time.
So that is really
And this water
interesting.
is ice cold, bubbles, you can see it as you walk closer to it, especially when the water's low, but it bubbles up.
So this is not a rare thing, that a spring can come up in a surface water body. And that's an interesting one. I knew there were some in the Potomac. If you'd be willing, if you know where it is and willing to email me like a GPS pin, I would love to know where that is. Again, those tend to be artesian because they come up when you see what we call pressure boils. When a spring comes up under that it has extra pressure, you can see sort of this boiling. And sometimes you can see we call them sand boils, and it's not that it's boiling temperature, but you just see little, it looks like boils, and the sand, if there's loose sand, you can see the sand roiling around.
Pebbles and rocks could be blowing around. It's a section that's about 20 by 30 foot.
Very cool.
Um,
Now, Florida has a lot of these
Yeah.
subterranean
Just
springs
gonna
that come up
ask
in
that.
the
Yeah,
ocean.
Boiling springs there.
Yeah, that's
Or-
boiling springs.
Technically, is that artesian wells in it?
Yeah, probably usually are. They're coming up with more pressure than the
Yeah.
water surrounding.
Yeah.
So I often call them,
Yeah.
artesian
Yeah,
spring.
There's a lot of, down in Florida like that.
Yeah, Florida has a lot of these because of the history of Florida, that the sea level was once lower. We have a lot of springs that come up out off the coast. Croatia also has those. Croatia's got some in the, Adriatic, and it's interesting because the Adriatic's so salty. Of course, the fresh water comes right up through it. And the history, the pirates used to come up and they would know where they were, and they didn't want to come to land because they might get attacked. Somebody would grab them. So they would know where these freshwater springs were, and they could go and just anchor and fill all their water supply out in the middle of the Adriatic by knowing where these springs were. But Florida has also that history as well. I don't know if they have the history with the pirates like the Adriatic. The other, you mentioned the temperature difference. One of the things that when I was working down in Kentucky in my consulting days, Kentucky, Tennessee, we were working on a military base, and they wanted to know where the springs came out in a reservoir. But when you got the military helping out, take a helicopter up with infrared photography and you find them, because in the winter, the surface water is cold, the spring water comes up warm, it comes up to the surface, and you can map them using infrared. And that's been done plenty of places now, but it's kind of like, you can see vernal pools that way sometimes too, particularly in the winter. The neat technique. A lot of questions?
Do you have any business cards? Because I have a friend who does have a spring on the property. They've got the spring house, the stone house, and it's off of Back Creek Valley Road. I don't know if maybe it's
Interesting,
been there.
because Back Creek Valley doesn't have a lot of karst and a lot of springs
Well, they've got.
in it, so that'd be
Yeah,
interesting.
so if you had a card, I can give it to her and.
I don't have a card, but you can get my name on this, and there's no anonymity for university professors, so if you Google Dorothy Vesper, you'll find me very quickly.
Okay, thanks.
And no, I'm not related to the Vesper sparrow. We just both like evenings, I guess.
Doesn't the Nile River start with a spring in Uganda? I think there's a kind of argument about it, but I actually was in Uganda and I went to the spring that is supposed to be the beginning of the Nile River. And then there was an argument about, no, they just said that, it's really somewhere else, but it's actually a spring. that
I
comes up.
can't answer that in any definitive way.
Okay.
That sounds like politics, that.
But
But it's pretty cool because.
yeah, it wouldn't surprise me, and I think I've read some things along that line, but I just have never paid enough attention to that area to know for sure. Well, ultimately, you could say almost everything starts as a spring. Headwaters tend to be springs in that water tower of West Virginia.
Oh, right.
Okay.
We'll never drink water and fight the same.
That's good and bad, depending on how you wanna look at it.
Would you say that water coming from a spring, like, I drive up to New York State often, and in the mountains in Pennsylvania, and you see the water coming out, is that safe to drink?
The roadside springs?
Yeah. I'm
I'm
saying no, don't do it.
Okay, so I spend a lot of time thinking about springs, as you can see. I drink very little spring water. You cannot tell by looking at a spring whether it's good quality or bad. So there are springs that are chemically like this, they don't change. A major hurricane could come through in the spring, chemistry doesn't change, and those are gonna be pretty safe. Because the water's flowing slowly, there's probably a lot of filtration of the water along the way. There's also a lot of springs that the chemistry changes tremendously, the temperature changes tremendously. So if it's a spring that you've ever seen be turbid, I wouldn't drink out of it. If you have a spring on your property and you wanna know that answer, what I suggest landowners do is you can buy very inexpensive little waterproof temperature loggers. You can buy them for $30 on Amazon. Put them in your spring and see how consistent is your temperature. Because temperature is gonna do the same thing that chemistry does in the sense of if your temperature flatlines, your spring's probably not terribly influenced by activities at the land surface. Okay, because by the time the water gets to the spring, it has become thermally equilibrated with the geology. It's also become chemically equilibrated with the geology, which means it's had a slow enough flow time. So if the temperature is a flatliner, it's probably okay. Or at least it's one I trust more. If your temperature is going up and down with every rainstorm, it's getting a lot of influence from the land surface.
Yeah.
And again, if spring gets turbid after a rainstorm, it's being influenced by the land surface. And I would not drink out of those without treating the water. So that whole roadside spring thing.
It just looks so good.
It does, and I meet lots of people filling bottles at
Where
springs.
Pole Steep lives up in Pennsylvania at,
Pine Grove
Pine
Farm
Grove
State Park.
State Park. There's
It's
some of
a
those.
big rock formation
Yeah,
called
yeah.
Pole Steeple and there's a.
Yeah,
little elevation.
I know
Up
Pine Grove.
there, a pipe spring and come up the
Yeah.
mountains, just go up the water, and stuff out, and spring out whether they treat it or not.
Well, they're still with us, as
Yeah.
far as we know. I mean, a lot of people do it, a lot of people swear by it.
Yeah.
I'm cautious, unless I know.
The same thing.
Berkeley Springs is a deep flow. You know that water's been underground since before they were testing the bomb. I will drink that fresh.
Yeah, we have.
Actually, I think Berkeley Springs water is really the best. It's my favorite spring water. I admit, it's true. It's awfully good. There's one spring in Monroe County that's on par, called Sweet Springs, aptly named. Yeah, you can see Sweet Springs bottled water all over the state.
Well, thank you so
Okay,
much.
well.
See you next month, if not earlier. Kathy Hilton with Generation to bring some free calendar. If you would like a calendar out.
Oh, it's just, so just yesterday, you mentioned those beautiful springs.
Oh, yeah.
I took that during my dog walk. Yeah.
My wife's name
Oh, okay. So,
I knew it would be, but it was amazing.
And how did your parents?
Yeah. Very well. But yeah, but they loved it. I know they went and reviewed the spot, they suggested.
Interesting.
Having donations. Like overheard me.
yeah, no, I was.
I was a little surprised.
Yes.
So now all the first one they're putting- So, cleaning that, I just- We're really-